So again, this is one more question on hybridization. This is the last question you'll get on hybridization before you see the exam. So now we're talking about hybridization of two different atoms in a molecule. So we're looking at this carbon atom here and this nitrogen. So using the rules that we've learned in terms of doing this quickly, let's see if you can get these answers in quick. So let's go ahead and just take 10 more seconds on this question here. Your parents are free to help if they're here with you. Okay, excellent. Excellent job, 98% of you. All right, you're a lot louder with the parents here, so let's make sure we're still listening. Okay, so let's go over what we just established here. Carbon A is going to be sp3 hybridized. What is the geometry? What's the Vesper geometry there? Good, it's tetrahedral. And this nitrogen B here, that's sp3 hybrid as well. What's the geometry around that nitrogen? Trigonal pyramidal, right? We have to take into account the fact that there's that lone pair there. All right, so let's go ahead and switch over to the lecture notes and see what we just did here. And essentially what we just did was I had you identify 2 of 4 components that make up what's called the morphine rule. And the morphine rule is a set of structural elements that are responsible for the biological activity of morphine and other morphine-like drugs that have a similar pharmacological activity in terms of how they're active. So specifically, the morphine rule is a set of 4 components which start with the phenyl ring here, so an aromatic ring. The second thing you identified, which is an sp3 hybrid carbon. And then following that, we have a CH2 group here. And the last part of the rule is this sp3 hybridized nitrogen. So in terms of thinking about what this means, I said this is responsible for the biological activity of morphine. If we take a look at the morphine molecule here, what you can see is that it's a little bit more complicated than this structure that we see right here. But if I go ahead and highlight the residues in purple, you can see that it in fact does follow the morphine rule. And what this means is this is what allows morphine to actually bind into its receptor, which is a pain receptor, and block the feeling of pain. So that's a very important thing in terms of thinking about hybridization and geometry, because we've actually established a very important structure and shape, which is this morphine rule here, that if it's found in a molecule, as long as there aren't other parts of the molecule that are messing up that interaction, we can actually form a very tight binder into these pain receptors. So morphine, as you know, is a very potent painkiller, but you also, I'm sure, know that it's also very addictive, so it's only used sparingly in terms of treating pain in a general sense, and it's always used in very closely monitored situations in terms of hospital care.